Hello, good morning. You're doing well today. All right, so let me get us back to our slides. All right. We looked at a few examples for using conservation of momentum to solve the problem. Today we'll continue to look at a few questions, and then we will talk about static equilibrium, which is the last topic in terms of the rotational motion. Okay, so let's look at the first one. And this is a question where you have the planet that's orbiting around the sun. So the sun is here, and the planet is going around in this circle at two different points, right? Point B would be closest to the sun, and point A is further away from the sun. So how does the magnitude of the angular momentum at these two places compare? Right? Again, it's asking about L. It's not asking you about omega, it's asking you about L. All right, so I'm gonna go ahead and let us launch our poll, and we can vote here. You can take a moment to think about that. That is fine. Okay, all right, so let's take another 10 seconds. If you haven't voted already, please do so. All right, any last minute vote? Okay, let's take a look at this together. I'm going to end this. Here is our answer distribution. So pretty much tied between A and C. So let's think about, here we're talking about when external torque is 0, right? If there's no external torque, then the angular momentum of the system will remain constant. So here, if we view the planet and the sun as our system, there is no external torque. Whatever force they have between them is 0. And here, the sun is not the orbiting around itself. What is orbiting around is the planet, right? So the planet's angular momentum should remain constant throughout its motion, should be constant at different places. So LA, point A should equal to point B. So this one has an interesting application because if we expand upon the angular momentum, so how do we calculate angular momentum for a point particle? We said it's R, right? This is R pointing from the center to where the object is, and P, that point, the direction of the momentum is the direction of your velocity, which is tangential to the path. So this is R cross P, and you can see they're perpendicular, so I can write R cross P, the magnitude, into R times P. So RA PA is equal to RB PB. Okay. Now, if RA is larger than RB, RA is further, RA is larger than RB, so PA is less than PB. Now, which means you're talking about the same object, right? The mass is the same, velocity A is less than velocity B. So when you are closer to the sun, you're moving faster than when you were further away from the sun. Okay, and this is actually one of the Kepler's law, which we will see in when we do universal gravitation. That is a topic that will come up after we do static equilibrium. Okay, so that you can see this is an interesting application of conservation angular momentum, and it can relate us to our future topics.
So the only reason that like we're alive is because Earth is pretty much a uniformly circular orbit for the most part, because it means that our angular velocity stays relatively constant.
What do you mean we are alive because of that?
Well, because like, you know how in the car crash, when we were learning Newton's laws, you said that's like why we have seatbelts and stuff, so that our brains don't really get mushed in when we hit something. So like if our angular acceleration, I don't know, the picture just seems really like it'd be a really big difference at some points. So I thought that maybe that would mean that like it'd be like the same kind of effect, like you're just like standing up while it's normal, or like while it's closer, and then when you get farther, or when it's far, you stand up and it's like normal, but then when you get really close, it just gets like super fast. And
yes, in fact, we do. The Earth moves faster when it's closer to the sun. The Earth moves slower when it's further away from the sun, because our orbit is not a perfect circle. This is a ellipse. But the thing is, this is a very dramatic drawing. In real life, is not the RA and RB is not that different. But there is still a closer point where you're closer to the sun, and there's a further point. That is true. And there is a difference in the velocity of the Earth. However, that does not affect us. We're talking about velocities, right? We're not talking about angular, we're not talking about acceleration. So as far as we are concerned, we feel perfectly fine as long as it's a constant velocity. It's when you suddenly stop and suddenly accelerate where we feel really uncomfortable. Like if you get thrown up and down in the roller coaster, well, that's a problem. But if you're just moving with a constant velocity, in physics we call these are inertial frames, so that we cannot really tell which inertial frame you're in. You can't really tell you're in inertial frame which moves at 1 meters per second or 5 meters per second. We can't really tell the difference. Our body couldn't. Just like when you're sitting in the airplane, if it's traveling super fast, right? But if it's really smooth, there's no bumping in the air, you don't really know that you still know you're in the airplane. But if you don't look outside, you think you're just in a regular house, or because all the physics laws is still the same as if you were sitting here on your chair. When you pour a glass of water, everything is still the same. So the fact we move a little bit faster along with the Earth is not a problem at all. Does that make sense?
Yeah, thanks. Sorry, I was just thinking about like the acceleration to get there. I thought that it could be such a problem that it would impact us, but I guess not. Okay.
Very good. Thank you for that question. Very, very intriguing. Okay, all right, let's look at another question. Here we have a star, since we're on topic of talking about planets, with star arrangement rotating with a period T. Over a period of 1,000,000 years, a long time, the radius decreased by a factor of 2. So the size of the planet is decreased, become 1/2 of what it was. So what is the new period of the star? What is a new period of star? So here we're treating the star as a sphere. So that's our model. And we know the rotational inertia for a sphere is 2/5 mr squared. Okay, so what would be the new period? So again, let's think about treating that as the angular momentum of the star should remain constant, right? And angular momentum is I times omega. So I initial, omega initial should equal to I final, omega final. So now the size has changed, right? Which means how fast it moves will also change. And how would that relate to the star's period? Let's take a moment to discuss this. For this question, let us go to our breakout rooms for a couple minutes, and then we will come back to them. I think I'm, we said it's room 4 last time, I believe. Now we'll be joining room 5 today. All right, so take a screenshot if you need before you head out to your breakout rooms. Hello, how's everyone doing? What do you think about this question?
Hello.
Let's talk about it together.
Can you clarify what it means by when the radius decreases by a factor of 2?
Meaning that our F is 1/2 of our initial.
Oh, okay.
Okay, so the size becomes smaller, which means IF is going to be what times I initial? The rotational inertia is going to be I initial times what fraction is our new rotational inertia?
Would it be 1/5?
Yes, 1/4, right? A quarter, because this is I is R squared. So if R is 1/2 of what it was, then I is 1/4 of what it was. Yes, very good. So if IF is 1/4 of I, then how does omega F compare with omega I? Do you think the star is now spinning faster or slower?
Wouldn't it be speeding up faster since it's now closer to the center?
Yes, so it is now more the mass are closer to the center. So I decreased. So omega will increase. Very good. And an increase to be exactly 4 times what you had, the velocity you had before. Okay, very good. We're now really close to answering the question about the period. So if you're spinning faster, do you think it will take you more time to complete one cycle or less time to complete one cycle? You're spinning
Less time.
less time, right? So T would be exactly 1/4 of your T you had before. So T final is 1/4 of your period before. And remember how T and omega are related? T is, or I could say omega is 2 pi, the change in angular position over the time in one round. So 2 pi over T is omega, okay? So if omega final is 4 times omega initial, then T final is 1/4 of T initial. All right, very good. Thank you all. I will see you shortly when we return. All right, 10 more seconds. Let's do for 10 more seconds. All right, I'm gonna go ahead and close this, okay. All right, so that's our distribution. So it looks like we all agree on the factor. It's a factor of 4, right? But is it 4 times of the period before or less of the time of the period before? So I would encourage us, all of us, to, when we answer questions, whether it's multiple choice or try to a long problem, think about qualitatively what this would be. When you plug in numbers, you get an answer. But just in case we made a mistake, let's think about qualitatively. Just make sure that we have a double check of our answer. So here the star, we know the star certainly decreased in size. So the star decreased in size, the rotational inertia decreased as well, right? Or increased. If R becomes smaller, then certainly it collapsed. M still the same, then R is smaller, I will be smaller. So if I become smaller, do you think the star now rotate faster or slower?
The star should should rotate faster.
Yes, very good. So omega increased. If it's a question about what is your new omega, you would say yes, increase 4 times as the omega before. But now it's asking about the time, the period. So as you rotate faster, how the time it takes for you to complete one revolution is now longer time or shorter time if you're spinning faster. More time to go around or shorter time to go around?
If you're going faster, less time.
Yeah, less time, right. So we know that we should get a less time than we had before, a quarter of the period, but it's not 4 times. Because when you're setting up the equation very well, you might just flip numerator and denominator or something. But if you do a qualitative reasoning before you do the answer, or after you get the answer, you can double check whether you get that correct. So it's t over 4, which is a quarter of what you had before. Next, I wanted to take a look at this homework question. It was homework 13. It's not something that's due yet, but it's coming up. It has to do with modeling the ice skater. Now, human bodies are complicated shape, but here we attempt to model that by treating our body as a combination of approximately a cylinder and rod. So let's take a look at this question together and we'll solve it together. First, they tell you about different parts of your body, what percentage of your mass at different parts of the body. So arms and hands together, 13% of your entire mass. Head is 7%, and the trunk and your legs is 80%. So we model a person, an ice skater, with our arms outstretched as we treat our body, okay, the trunk, legs, and head all together is a long cylinder. And the 2 arms are 2 rods extend out. So you have a cylinder and 2 rods. So this is how we're going to model the body. And now there are some numbers. The mass of the person is given, the height of the person is given. The length of the arms is given. And the diameter of the trunk is given. And we know initially this is 81 RPM, rounds per minute. So we just gonna keep our omega this way. We know you can change this to radians per second, but we don't have to convert because your omega-2 is also, you need to give it in the unit of RPM. So the unit is the same, so you don't have to convert. So by initially have the arm stretched out, but then bring it closer to be part of the cylinder, the object has changed its shape, right? And changed its rotational inertia. And what is your new angular velocity? So basically that is the question. Let's first define some quantities, right? There are a lot of information here. Let's write down what are the given quantities that we know. So these are the givens. Okay, so the mass of so here I'm just treating the object as I'm gonna call different parts of the body as its shape I'm going to model. I'm gonna call the cylinder, it's the head and the trunk, and the legs. The mass of the cylinder is 87%, because that's the head and the body combined. So 87% of the mass of the person. Okay, so I have that relationship. The mass of the rod, this is one of your arm. You have 2 of the rods, one on each side, is 1/2 of that 30% of the mass of the person, because 2 arms together is 13%. So 1 rod is 1/2, 13% of the mass of the person. See, I'm not quick to calculate these numbers yet, because I want to see how much I can cancel and reduce. So I'm not going to worry about canceling or getting my numbers right yet. Okay, and then it tells me the length of my rod is 74 centimeters. So that is the L of the rod. Okay, so I'm going to use L to represent the length of the rod. And this is the height. So this is the height of the cylinder, which is 1.5 meters. That's the height of the person, which is height of the cylinder. And here you have a diameter of the cylinder, which is 37 centimeters, okay? So these are all the known quantities I have at this point. All right, now let's draw some pictures to visualize what happens before and what happens later. So we're gonna look at initial. So initially, I have a cylinder with this diameter, with this height, and on two sides of the cylinder, I have a rod. Sorry, should be the same length. The rod has total length of L, and I know the mass of the cylinder, right? I know the mass of the rod. So originally, I have such a distribution. So you can see what is really different from initial to final is your rotational inertia has changed. So let's calculate the rotational inertia for our initial and final. This is my initial. I know my initial rotational inertia is the cylinder plus the rod. And I have two rods, right? So two rod. Okay. Now, cylinder is easy, right? What is cylinder? Cylinder is simply 1/2 m times radius r squared. Okay, mass of the cylinder is already given. I'm just gonna keep it as mc for now. Okay, r is half of the diameter, so it's d over 2, so d squared over 4. All right, so I have IC is 1/8 mc d squared. Now the rod. Okay, so the rotational axis is here. You're rotating toward the center of your body, right? You're rotating like that. But the one, what we know about the rod is we know that according to the center of the axis, center of the mass for the rod, the rod relative to its own center of the mass is 1/12 m L squared. So this is a formula you can get from our book, from our notes, from a reference. All right, but that's not what you want. Your arms are not rotating on its own, it's rotating relative to this axis. So what do? I use the parallel axis theorem. Remember, the new rotational inertia relative to this line is the center of the mass plus m times the distance squared. So I of the rod, what I need is this one plus this distance. This is the distance between these two different axes. Okay, and what is that distance? You can see that is your half of your length of your rod plus half of your diameter. So that is a distance. That is d over 2 plus L over 2 squared. Okay, d over 2 plus L over 2 squared. I did notice that it just so happens that the numbers are given in such a way. My length L is twice of my diameter D. So L is 2D. So I decide to, okay, well, I'm going to use simply one variable because that helps me further to write it shorter terms. I can cancel out more of these terms. So I'm thinking, okay, well, how about I'm going to replace everything using D. So I'm going to replace L using 2D. So I will do that. I will say this is 1/12 mr. L is 2D, 4D squared mr. So L becomes 2D. So this becomes D. So it's 3/2 D squared. Okay, so that becomes 1/3 mRd squared plus 9/4 mRd squared. And you can group these together, becomes 12 on the denominator. So that becomes, okay, 4 plus 3 times 9 mRd squared. So that becomes 31/12 mRd squared. Okay, I agree that is a lot of calculation, but we just need to be careful and wait for the end when we can cancel everything. So that is for the rod. Okay, so you can see I found the rod. Now I can bring it back to my original equation to find the total rotational inertia. I initial is now IC 1/2 mc d squared plus 2 times of the rod. Okay, so 2 times 31/12 mRd squared. That becomes 6. You might wonder, why can't I just plug in numbers at this point? You could, if you feel that is easier, you can do that. Okay, so this is the hard part. That's just the only hard part, because the final is easy. The final is you put your 2 rod and close it to your body, you become a big cylinder. So I final is easy. I final is simply you just become this big cylinder. The diameter didn't change, the height doesn't change. Just the mass now is the mass of the entire person, because now your entire person become a cylinder, right? So I final is simply 1/2 mass of the person times d/2 squared, r squared. So it's 1/8 and p and mass of the person d squared. So that's it, that's your I final. So now we are ready to plug this into our equations for conservation of angular momentum to get the new omega. So use I omega to be a constant, right? Okay, what is my I initial? I just got it here. Okay, so 1/2 mc d squared plus 31/6 mRd squared times omega initial is equal to 1/8 mass of the person d squared omega final. So you can see the d squared cancels. Would it be nice if we can cancel some mass as well? So you can plug in these individual masses at this point if you like, or you can see, well, actually all of these masses are related to the mass of the person. So why don't I replace them with the corresponding percentages? So mass of your cylinder, that's your head and trunk and your legs, are 87% mass of the person. And your arms, one of the arms is 1/2 of the 30% mass of the person. And 1/8 mass of the person. So here, what I want to do, I want to cancel the mass of the person as well. And I'm getting my omega final now. My omega final is equal to 1/8 times 0.87 plus 31/6 times 1/2 times 30% divided by this 1/8, right? 1/8 times omega initial, which is 81 RPM. So you can plug in numbers at this point, and I think the calculation is much more doable plugging in here rather than doing it earlier. Okay, so that is the answer, and then the final result is somewhere around 288 RPM. So you spin much faster by bringing your arm in. Okay, so that is, you will get different numbers but if you follow the same process, you should be able to solve this.
Professor, can you go back to the previous example?
Here,
The one about the period of the star.
here.
Yeah. What happens? So maybe I missed it, but when we were talking about the different the angular velocity increasing,
Mhm.
did we account for the actual length the star has to travel changing? Because now it has to travel half as much and it's going faster, or did we account for that with the 4t?
I don't quite understand the question. I think if omega is 4 times of omega I, so here we're just talking about rotating
Yeah.
around yourself,
Mhm.
a spin around your own center of mass axis. So, right, if I'm spinning faster, wouldn't t, because t is 2 pi over omega, right?
Mhm.
So if omega is 4 times, then t will be 1/4 of what you had before, right?
Oh, okay. Sorry. I misunderstood the question initially. I thought it was a rotation around like circular rotation instead of rotation around itself. Okay, cool.
Okay, yeah. So
Thank you.
yeah, because we're using the I relative to its own
Yeah.
center. So yeah, we know Earth is rotating around ourselves, itself, and then also around the sun. We're just talking about around itself. Yeah.
Thanks.
Okay. As far as this homework questions, any questions about what we just did? About our solution?
I have a question.
Yes, go ahead.
The equation where you're finding the inertia of the rod,
Okay. Yeah.
that's root over 12 mRL squared.
Mhm.
That second part where it's the mass of the rod
Mhm.
times the quantity.
Mhm. You mean right
Um,
here? Yeah.
Yes.
Okay.
So I get that L over 2 corresponds with the mass of the rod, but how come D over 2 doesn't correspond with the mass of the cylinder?
Are you asking where this term comes from?
Yeah, so what I was thinking originally was it would be mr times L over 2 as one quantity plus mc times D over 2, since
Oh,
D over
this is
2 goes with the cylinder of the
just
mass.
this distance. So, okay, so I wanted to maybe write it here. I'm using parallel axis theorem that if your rotational inertia relative to this axis is I center of the mass, but you're not rotating relative to this axis, you're relative to rotating to here. So this is your new axis, but these two axes has a distance between them, right? I call it S. So I know what I'm trying to say is relative to the new axis is relative to the center of the mass axis rotational inertia times ms squared. So here, the rod is rotating relative to this axis. So that I is the I relative to the center, which is here, this blue line, plus the mass of the rod times the distance between these two axes. And that distance is, you can see, is half of the D plus half of the L. So here I'm doing the rod. It doesn't have anything to do with the cylinder.
I think what I'm asking is for the M, you're only accounting for the mass of the rod, not the mass of the rod and the mass of the cylinder that corresponds to D over 2.
Right, because I'm calculating the I of the rod. So I'm gonna use mass of the rod and mass of the rod. I calculated the mass, the I of the cylinder where I use the mass of the cylinder. And eventually I will add these two together right here.
Okay.
Yeah.
Thank you.
Very good, thank you. Any other questions? All right. So this will be the last question we talk about for conservation of angular momentum. I want to give you a quick overview of everything we have done so far. And then I'm going to be very fast, but you can check on these notes later if you need a more detailed review. Is let's say we have a ball rolling down the ramp. We're talking about rolling without slipping. I'm going to show dynamics, applying kinematics, energy, momentum, and conservation momentum. Now, only these three are what we would expect you to do. Applying these two are not going to give you new information. Conservation momentum are going to give you the same thing as dynamics. Conservation of angular momentum going to give you the same thing as your dynamics in rotation. But I want to show how you can apply the 5 different approach to the same problem. We have done this already for rolling down, object rolling down using dynamics. So this is sort of like another review. So when you're rolling down ramp using a dynamics approach, we need to draw force diagrams, right? So there are 3 forces: gravity, normal force, and we definitely need static friction. So this is static friction. It's not kinetic or it's not sliding, it's rolling. And you definitely need the static friction because without the friction, you're not going to have that torque to make it roll. It's just going to slide down without that friction. Okay, so dynamics approach, you do Newton's second law. So we apply Newton's second laws both for translation and for rotation. So 2 of them, right? F equals ma is easy because that's mg sine theta is the force down the ramp. Static friction is up the ramp. That's the only way to make it rotate it clockwise. So it's down the ramp is equal to ma. Acceleration is the linear acceleration down the ramp. And if we apply Newton's second law, torque equals I alpha to the ball, we can see, well, the force that's applying the torque is a frictional force, and it has a level arm of radius r, that's the radius of the ball. And it's making it rotate clockwise, and that's a negative direction. So I put a negative sign on it. I of the ball is 2/5 mr squared, and alpha is the angular acceleration. So angular and linear acceleration are related by a radius r. We have talked about that. So if I replace alpha by, if I replace r times alpha with a, from this equation, I get frictional force is 2/5 ma, and combine that with my Newton's second law for translation, I found my acceleration. So this is the acceleration of the ball going down the ramp. So this is, if you take a dynamics approach, you get this. Combine that with kinematics, you can find how fast the ball is moving at the bottom of the ramp, simply using kinematics equations, right? This is constant acceleration, initial velocity is 0, final velocity square is equal to 2 times acceleration times the total distance it traveled along the ramp. So I plug the acceleration I found, I plug the distance, which is h over sine theta. I found this is the final velocities. It's probably much easier to solve this problem using a energy approach, and we have seen this multiple times. This is really just a transformation from gravitational potential energy to kinetic energy. The only difference is now we have 2 parts of the kinetic energy. One is your translational, one is your rotational kinetic energy. The rotational velocity, if it's rolling without slipping, we said is always v is equal to r omega. So you can replace your omega using v over f, and you can find your velocity at the bottom of the ramp. So you can see this is a much easier approach, but it gives you the same result as the kinematics and dynamics approach. So if there's an exam, I would expect you to be able to solve it using either energy or a combination of dynamics and kinematics. But we can still apply momentum conservation to this, even though that's not something we usually do, but you can do this. And it's not gonna give us anything new. So if we apply momentum conservation, the final momentum is mv, initial momentum is 0, and the momentum impulse, the momentum transfer is force times time. The change in momentum is only in the x direction, right? So I only need to account for the force in the x direction. And velocities is really acceleration times time. So you can see the momentum conservation give you F equals ma, which is nothing new than Newton's second law. So at this point, you will start with doing Newton's laws again. But you can, if you want to, apply a momentum perspective on it. Finally, what if you wanted to talk about angular momentum? You could. The angular momentum initial is again 0 because it wasn't rotating at first. The angular momentum final is I times omega. And the angular momentum change is the applying the torque for some amount of time. So torque is R cross F. So we already talked about how to calculate torque, and you plug in the time. And again, you could write your velocity over time to be your acceleration. You get a relationship between your frictional force and your acceleration. Again, this is nothing new. This is giving you the same result as your Newton's laws for rotation has given you. But because they are all related, right? D tau over dt equals L gives you conservation of angular momentum, right? And that gives you the same thing as you had before. So I just want to show that you can apply everything you need, everything you have at your toolbox right now to the same problem, and they should give you the same result. But in exams, focus on the energy approach and the dynamics and kinematics approach. Don't worry about the momentum and angular momentum part. All right, so that's all. We're going to end our discussion for rotation. Right now, what's left is nothing is moving. We call it rotational statics. If we were doing rotational dynamics before, right now it's statics, meaning that we don't want anything to rotate. We want things to stay still, not moving, not rotating, simply in static equilibrium. This topic is a new topic. However, all the physics you have already, you know all the physics. So essentially, we're not really doing anything new. So this is the old physics. Basically, if you want something to be not translating, you needed to have a 0 translational acceleration. A should be 0. If you want something to not start rotating, you wanted to have a 0 angular acceleration, right? Not moving this way, not rotating this way. So both of these are satisfied, then you reached a equilibrium. And you want to have that equilibrium in many different things. For example, your ladders, your balance beams, your bridges, your buildings. You don't want any of these to move. You want them to be in static equilibrium. So you want all the forces to be 0. You want all the torque to add up to be 0. So that makes sure that both of these accelerations are 0. So that's it. That is the old physics we're going to do in this section by making all the forces to cancel and all the torques to cancel. Okay, so for example, you have done this question already. We're trying to balance a beam and a ball. Is it possible to balance them at this point? Let's see, you have a pivot point right here, and you're putting a object M here, right? So you have an mg force down this way. The rod has the same mass. So right now we want to see, is the object balanced? Okay, first of all, is the force balanced? Let's see, you have two forces. One is the ball is mg, the other is a rod. The rod has a gravity mg as well, and it's acting from the center of the mass of the rod, which is halfway of the rod, right? So right now here. So the force is balanced, right? 1 mg here, 1 mg here, and the pivot point could provide a 2 mg here. So it's possible to balance the force, yes. What about the torque? Is it 0? Well, if we view our rotation relative to the pivot point, this mg is trying to generate a torque that going to be counterclockwise, and this mg trying to generate a torque that going clockwise. And that torque, one is mg times level arm L over 4, and the other one is also mg times L over 4, right? The same distance and same force, so the torque is also balanced. 2 mg is right at the pivot point, so that doesn't give us any torque. So you can see, yes, actually, it is possible to balance this setup because all the forces and all the torque, they are balanced. All right, so we are out of time today. I will see you for, Friday, and we'll continue to do more questions on static equilibrium. All right, have a good rest of your week. See you next time.
Bye, Professor. Thank you.
Bye-bye.
Have a good week. See you later.
Thank you, you too.
Professor,
Yeah,
would you mind going back to the star problem?
okay, the star one,
Yeah,
this one?
yeah. So I think I'm getting it confused. So for this particular problem, how would you know that the angular momentum is conserved? Like, I know we don't have torque necessarily, but I'm still kind of confused on that concept for this problem.
So does it say there's any external forces? You know, if it doesn't say there's any external forces, there's nothing for you to think there should be, because the star, especially for a star, it's just there. And around with its surroundings, there's nothing. So if it's just there by itself, then the torque external is 0. So torque is dl dt, right? So if torque is 0, then L is constant, which means the angular momentum does not change, right?
Okay,
Yeah.
I see. And so when we applied, okay, I understand that now. And then when we said that it was that our radius is 1/4.
One half.
1/2. Oh, sorry, I meant 1/2. Yeah. And we plug it into the equation. I'm confused why our final momentum would be 1/4. Sorry, why our initial momentum would be 1/4.
Okay, you mean
Okay.
T is 1/4?
Yeah, so like, so you know how we
Right.
put in our 1/2 radius into the equation for the inertia of the sphere?
Right, so I is 1/2/5 mr squared. So if radius is becoming 1/2, then this is 1/2 squared. So final rotational inertia is 1/4 of your inertia, right? Because it's radius squared, right?
Right. Okay.
So
see.
yeah, so this has become 1/4 I initial, and I cancel my I initial, then omega final is 4 times omega initial, right?
Okay, yeah. And then since our, okay, I see. And
Yeah.
so since our omega is 4, and the period is the velocity over the, I
Yeah,
mean, sorry,
so-
the period of rotation over velocity.
Yes.
Okay.
So
I
you
see.
can say, okay, velocity is displacement over time. So omega, that's how
Right.
we define omega. 2 pi, change of position one way around 2 pi over the total time takes the period t. So, you know, that's why if you write t, then it's 2 pi over omega. Okay.
Okay. Okay, thank you, Professor.
Sure.